Alright, so let's continue our discussion. There are a few other kind of imaging systems that I wanted to discuss. Another one was called 4-pi confocal microscopy. It's related to confocal microscopy, but it has some advantages. Okay, so if you remember confocal microscopy that we discussed a few minutes ago, you have light coming in, focused inside the sample, and light comes back, right? So the range of this angles of light that you collect determines what your resolution is. And your light is coming in from one direction, back from in the other reverse direction. So that is the nature of this confocal. So the so somebody recognized the fact that if you collect more and more angles, then you can get better and better resolution. So you can have a larger lens which is focuses onto a tight spot, and light you collect more of the angles of light that comes out, right? So with like this is what's called high NA, high numerical aperture lens. So higher the NA you use, the best you can do in air is 1. And if you can't do, if you don't want to get better than that, you put water immersion. So the medium here can be water, and that way you can get even better NA, and then you can get even higher if you put some oil of some sort. Okay, so that way you can collect more and more angles of light that comes back and gets focused. So 4-pi is takes the step even one further. Not only do you collect light that comes backward, you collect light that goes forward and back. So you collect both, right? So it's kind of like so 4-pi is the solid angle. That the entire solid angle, if you remember, that we took 2-pi is in 2 dimensions, right? But in 3 dimensions, it's like 4-pi is all the possible angles where light goes, right? So if you collect all the light that goes in all different directions, that is 4-pi microscopy, and that gives you as good of a resolution as possible with like with the diffraction limited light. Okay, so in fact the PS is given by the product of illumination and detection, and the main idea here is we increase the aperture angles and to get much better axial resolution and like than confocal microscopy, and both illumination and detection aperture are increased. So this is kind of like the instrument, what the instrument looks like. You have just like a regular confocal microscope, except for light comes in and goes back this way, and comes in and goes back this way as well. So there are two different directions in which light can you can get to collect light from both different directions, and that way you can get much higher kind of the sample, like you can get the most amount of angles, and that way get the best resolution. Okay, so here is kind of the comparison. This is the regular confocal microscope, and this is like it's an oval shape, right? XY you get good resolution. Z it's a little bit worse resolution. It's because it's longer. The point spread function is elongated. That's the nature of light focusing. But because your light coming in from both directions, the point spread function is narrowed and it's even smaller, especially along Z, right? It's both along XY and Z, but the Z1 matters a lot more, as you can see. So instead of this being your resolution in confocal, this is your resolution with this 4-pi confocal. So this way you are now like increasing the range of angles that you collect, and that way you are getting much higher resolution of image. Yeah, so this in essence is like, so all these kind of approaches are diffraction limited. So what is diffraction limited? So when light focuses onto a small spot, there is a smaller spot that you can make, and we are using that size of the smallest spot to do images. If you can kind of get measurements that get the resolution better than the smallest spot, That is called super resolution. Okay, so there are several techniques which allow us to super resolution, which we'll get to in a few minutes. But so this is the almost like the best we can do given the diffraction limit and some of these kind of constraints. Any questions about this approach? Okay. So another kind of approach which like aims to break the diffraction limit. So in other words, um, it's like how do you get better information than the diffraction limit? So we are heading towards how to do better and better, get see smaller and smaller things. So the diffraction limit is kind of a fundamental limit because of the nature of the wave nature of light. So is it possible? So for about 100 years, so the person who figured out the diffraction limit was a scientist by the name Abe in the 1800s, and uh, Carl Zeiss, who was and Abe were the two people who, like, in fact, Zeiss is even, like, he was a German who started a company whom they make microscopes, and they were trying to make better and better microscopes, and they were trying to figure out what's the limit of what the best we could do. And even today, the company exists. Carl Zeiss is a company out of Germany, and so at that, even in the 1800s, they figured out that they figured out that there is a limit to how good you can make a microscope, and that's the diffraction limit. Okay, but for 100 years, people thought you simply can't see better than small things smaller than the diffraction limit of light. But just in the recent past, people, like in the past 20, 30 years or so, people have figured out how to break this fundamental, what was thought of as a fundamental diffraction limit. Okay, so that is the entire field of super resolution microscopy. One of the ideas that people have come up with is this. Okay, what's called structured illumination microscopy. So the like the idea is something like this. Okay, so instead of having, so let me show you in terms of pictures. So you have an object, you make an image, get a microscopy image of this object, right? So now, instead of, so this is a regular image. Instead of, and so you have white light incident on this. Let's say a plane wave is incident on it, you get an image, you get data. Instead of plane wave, just regular light incident this way, what you do is have uh, so basically bright and dark, bright and dark, bright and dark, bright and dark pattern. A pattern light, a structured pattern light incident on the object, and then you do the microscopy. So why is this interesting and why is this useful? This pattern is something like cosine of y, or something like k. Let me write it this way. This pattern of illumination that you use is something of this sort. It's k y y. Okay, it's a cosine function on top of the object. So if let's say S is your object, S of x comma y, what you do by illuminating with this structured light, the structure is a cosine function. Okay, so what the idea in fact is kind of was because of the Fourier, like people once they understood Fourier optics, they came up with this idea which was take the sample xy, S of xy, multiply it by, have this light in cosine in kyy incident on it, for example. So what happens is S becomes multiplied by cosine of kyy. So when you multiply by cosine, what happens? So when you multiply a signal by cosine, so you might you might remember this from your communication or signals class. Cosine t, cosine omega t, omega naught t. Exactly. It gets shifted to the location. Right? Exactly. So this is used, the idea used in radios and a lot of other situations, right? One-dimensional signal, say it's a function of time. So this is the frequency spectrum. So if you have a cosine in like Fourier transform for cosine is say omega naught and minus omega naught, right? It's a delta function. When you multiply in the time domain, you basically take this and make a copy here and make a copy here, right? So shift in the frequency domain, you shift it to the location of the delta function. In other words, your frequency shifting this way and frequency shifting this way. So imagine, like, take an object which has a range of frequencies, you shift it here. So the diffraction limit is equivalent to you only having access to some small range of low frequencies. There is a diffraction limit in spatially. That in frequency domain, it means there is a ring of spatial frequencies. It's a low pass filter in the frequency domain. The process of light propagation is doing a low pass filtering to your light. So if you do frequency shifting, what happens? Let me erase this and get So what happens is that your object is in the frequency domain is like this. You have shifted it here. So the frequencies that were high frequencies that were here. So if your origin is here, the high frequencies that are here is now inside the field of view in the Fourier domain. So you have shifted the frequencies so that what were previously high frequencies have come to the low frequencies. So let me try to explain that again. Okay. So let's say the object has some low frequencies here and high frequencies on here. So now if you shift it, let me draw it in this way. You shift it a little bit. Now what was a low frequency has come inside the circle, and so you can start making a measurement. Okay, so the high frequencies which are previously lost because they were outside your diffraction limit, outside the range, have come. You have shifted it so that they are inside now. Okay, and the low frequencies, like some of them have gotten out, but low frequencies went out, but the high frequencies came in. And that's the idea. Okay, so it's the same idea as, like, say, like it's the Fourier, like one of the Fourier properties is multiplied by cosine shift frequencies. That's it's used in radio, it's used in television, it's used in our communication systems for kind of, say, what's called modulation, frequency modulation, kind of. So it's the same idea that people figured out in optics. You can do the same thing as well. Okay, so multiply by cosine. So that way you shift the frequencies and then make a measurement, shift it in a different direction, make a measurement, shift it in different directions, you make measurements. And that's the essential idea of this structured illumination method. So let me kind of elaborate on this a little bit. So let me actually get to this picture. Okay, so in the Fourier domain, in the kx-ky domain, say you have an object like this. So this is like, but the cosine function is like two delta functions over here. So when you multiply the object by this, it gets shifted to the right and shifted to the left. So what was previously like high frequencies over here, they become inside the, like when you shift it to this, like the high frequencies are inside the measurement Fourier domain. Okay, and similarly you shift it along this direction, shift it along this direction, shift it along this, shift along this. So you like this, like you collect this data, this data, this data, this data. So you put together all like collect data from different angles of illumination. So in other words, shine this pattern, shine this pattern, shine this pattern. For each of these patterns, collect an image, and you stitch them all together in the Fourier domain to get a much bigger, instead of this being your the spatial frequencies that are inside your sample, you have access to a much larger range of spatial frequencies. So what does that mean? If you add a lot of higher frequencies, you'll get a sharper image, right? You'll get better edges. So what happens when you have used, like, add up higher frequency components? The higher frequencies that you can use, the sharper your edge will be, or the higher, like the sharper your image will be. In other words, it becomes better resolution, smaller resolution. So how good of a job can you do? You can do double the resolution, or double meaning the value of the resolution is half. Okay, so instead of say 200 nanometer resolution, you can get 100 nanometer resolution. You can half your like the value of the resolution. So it's double the amount of information in every dimension. Double along x, double along y, double along z. Okay, so this is yeah. So this is basically you take a bunch of images, take the Fourier transform, put them in the right place in the Fourier domain, and then take the inverse Fourier transform. And that's so this is yeah. So like so the essential idea is people have been doing this for a long time in one dimensions in communication systems. Somebody thought, why not do this in two dimension optical system? And this gives you much better resolution than you would otherwise. Okay, so this is one way of doing super resolution, doubling your resolution better than the diffraction limit of light. Okay. Any questions? Not quite. The cost is you are getting not one image but like six or more images. You have to like take 6 images to get that resolution of taking one image. It's not penetration depth is not affected. Correct. Penetration depth is the same. What you lose is what the penalty you pay is. You have to, instead of taking one image, you have to take multiple images and do some computation to recover the data, the better resolution data. Okay. Any other questions? Okay. So this is kind of the, like in biological samples, this is the extent of improvement you can get. So if you just use a regular microscope, a wide field microscope, ordinary microscope, you will get something, image of the sort. But with structured illumination, you can see much finer detail that is kind of blurry in the previous case. So here is another example. So this part is what you get with a regular microscope. You can get much finer details with the structured illumination microscopy, or SIM. Okay. So this is how this approach works. The related thing is, so how do you create this kind of a cosine pattern? The way you can create a cosine pattern is take a slide source, put a grating here. So there is a zeroth order which goes through just like before, but there is first order this direction and this direction, right? Then you put them, like interfere them together. You have two plane waves coming together and interfering. Then it creates this kind of a pattern. Okay, on the sample, by interfering two plane waves, the interference, when you interfere two plane waves, it creates a cosine function on the sample, right? So that's how you can create this kind of one beam this way, one beam this way, make them interfere, and that's what you can do. So like if it is a linear process, then you get a perfect cosine function. But if you do saturation, so if it's a fluorescence kind of say the object is fluorescing. Now if you apply this two plane waves and there is an interference pattern, that gives you a cosine function. But if you expose this for a long time, or if you have excitation is high enough, then it becomes a non-linear process. So instead of it being like a sinusoidal thing, it like if you cut it off because of saturation, then you can get something close to like a square wave, not exactly a square wave, but something more and more closer and closer to a square wave. So what this means is, by making this narrower and narrower, you can get even finer and finer details. So instead of doubling the resolution, you can triple or quadruple by kind of using the saturation excitation kind of an approach. People have tried this. It's much harder to do because you have to saturate, like so kind of you have to maximize like sort of fluorescence as you increase the number of photons. See, you have some fluorophores inside of the sample, right? If you shine some light on it, like some of them get excited and then they come back down, right? So if you put so much light that all of the fluorophores are kind of getting to the maximum, then like at some point increasing the number of photons does not give you extra fluorescence signal. That means things are saturated, and that's like if you use that, normally it's a problem because it becomes non-linear. But you can use that to your advantage in this kind of situation and get better resolution than the diffraction. That's one idea. This this entire field of super resolution microscopy turned out that it's very important, and it's one of the kind of more important discovery of invention of the past 25-30 years or so. So in fact, in 2014, the Nobel Prize for Chemistry was given to these three scientists, Eric Berzek, Stefan Hell, and William Moon. I'll talk about what they invented in a few minutes, but basically this happens to have a lot of very interesting and useful applications in biology and medicine, and they were kind of, it was so important that they gave the Nobel Prize for this. Personally, I'm happy to say that like sort of I've met both Berzek and William Moon, and yeah, it was a true honor. So let me tell you what they did and what is the work that they did. Okay, so getting back to the basics. So if you have so if you think of the definition of resolution, which is like related to the diffraction limit. So if you have like one kind of one point spread function, which is your one blur, one diffraction limited spot. If you take cross section, in one dimension, it looks like this curve. And if you have an object which is second object which is here, then there is one dot, like one object here, a second object here, and if they are close to each other, but you can still see this peak from this peak, if you can separate the two peaks, then you can distinguish the two dots, and therefore they are like they have been resolved. And if they get close to each other such that you could almost resolve it, but just barely, then this is the diffraction limit. There are different criteria you can use for kind of figuring out the value of resolution. Rayleigh criterion is a very common one. The exact number is not very kind of like different criteria will have approximately the same number, but not exactly. But that is not the crucial part. But like the important thing is, when are they unresolved? If you have one kind of this, like if they essentially become one blob, right? Then you really cannot distinguish the two dots. So that is the fundamental limit of resolution because of the diffraction limit. What Eric Berzek and a few other scientists around that time figured out was that, let's say you have a diffraction limited spot. It has some shape, like sort of maybe a circle. It may be like circles with some ripples and rings and so on. Whatever the shape may be. The crucial thing is, if you know that there is one dot here, one dot here. If you just know that there is one dot, like one fluorophore, one scatterer, one dot from which light is getting emitted, even though this is a big blur here, you can figure out the center of that dot. If there is a blur and you know that there is only one emitter there, you can figure out this it's because it's a circle, you can figure out the center of the circle, and therefore that emitter must be at the center of the circle. It can't be at the corner of the circle or anywhere in between. So it has to be at the center of the circle. And therefore you can figure out, even though there is a blur, if you know that it is one emitter, then you can figure out the center and you can know the location very, very precisely compared to the size of the blur. And that is the crucial idea. Okay, so if you have one dot from which light is emitted, figure out the center of the dot, and there is a mathematical expression as to how precisely you can measure the center of the circle, center of the dot, and the answer is very, very precisely. Okay, so to a few nanometers, you can even if the size of this point split function is say 1 micron, but you can figure out the center to say 10 or 120 nanometers. You can figure out where the middle is very precisely. Okay, this is the central idea of his approach, which is called palm and storm. There are two different related ideas, but this is the crucial part. So then the question is, can you make one dot and this dot, if there is one dot here and a different dot far away, which is a different circle, it's okay. The only thing you have to ensure is two dots should not be very close to each other, so that they become one kind of blur. As long as within one measurement there is only one dot, you can find the location of the dot very precisely, and then the next thing is if you can make different parts of the the structure become emit light at different times, then you can literally connect the dots and make a measurement. Okay, I'll tell you how exactly they did that. Okay, so here is the basic idea. Let's say there are a lot of dots inside a sample over here. It's not easy to see, there are three kind of dots here, but you shine light on them, which is what's called a photo. These are photoactive molecules. So you if you shine an activation beam, some of them start emitting light. And now you use a camera and take a picture. You get an image of these molecules. Okay, if they are very few far away, scattered far away, and you can ensure that within one area there are not two emitters, only one emitter is there. Then you can find the center of this very precisely, center of this precisely, center of this precisely. So you can get the location of all these emitters, and then you turn off those molecules in some way. Okay, after you do the localization, you know the exact location, you do photobleaching. There is some process that was one of the things that they invented, was figure out, let's turn them off, then again activate it, and a new set of dots have turned on, and then you find the location of them, and so repeat this. Okay, so instead of doing it once, you keep doing this over and over again, and so every time, so you have a target structure which has some say thin fibers and things inside you want to see. So there are these dots which are emitting light. So do one localization, find the center here, then next time do another activation, another set of dots, and do a localization there, and keep doing that lot of times, and you construct an image of this stuff. Okay, so to show you graphically what that means, this is a pure simulation, but this is a blurry image which is a diffraction limited image. So now there are these dots which are turning on and off all the time from each of the points inside the sample, and you find the center of these dots very precisely and put it in this image over here. So as you keep accumulating the dots, you will get much better and better image. So compared to this blurry image, you can see how it's getting more and more precise. It's getting so you can get very, very high accuracy images, sort of this much better resolution than you could get with a diffraction limited blurry spot. So this basically is the central idea of how we can do super resolution with this are called palm. So there are few scientists who invented it about the same time. So So different people, scientists call it different things. So the PALM is basically photo-activated localization microscopy. Okay, and then STORM is stochastic optical reconstruction microscopy. So these a few different scientists came up with this, and I showed you simulations. This is actually real-world biological samples. So this paper over here that they showed, so you can create this blinking fluorophores. It could be induced by like some external excitation, like activation beam. It could be naturally blinking fluorophores. Instead of just having a fluorophore, create these molecules which blink, and like sort of, so only at any instant in time, only a few of them are blinking, and you find the center of each of these blinking dots, blinking circles. So you can find the dots, put them all together, stitch one after the other image, and connect the dots, and you get a much more precise image. So you can this is from the same paper. It's not the exact same data, but this is the kind of image. After you kind of all this blinking happens, you can reconstruct an image which is much finer details at a much higher resolution than and much lower than diffraction limit. So you can see things much below the diffraction limit of light. That is the great achievement of this kind of approach. Okay, so like this idea that you can find the center of a circle much more precisely than the actual the center is the crucial that kind of breakthrough that Eric Betzig and a few others figured out at that time. Okay, and other than precise localization, one of the key things that determines what the resolution is the density. So if say for example you want to achieve 10 nanometer resolution, lateral resolution, then the molecules must be at least 5 nanometers apart. So there is still a like new limit which is much smaller. 5 nanometers is like, imagine, like it's like like literally one or two molecules, right? Like sort of 5-10 nanometers is so small that it's a few atoms, few tens of atoms, so like maybe 100 or few hundred atoms at most. So basically, it's a very small area. So this is actually, these are what are called single molecule measurements. Literally, each one of these linking things is coming from one molecule. So you're isolating separate molecules and kind of you're connecting the dots and figuring out the at any given measurement, these kind of like it's basically a single molecule that you are essentially getting the data from. Like one dot corresponds to one molecule. So yeah, so as you increase the density of these locations of these fluorophores, you can construct better and better images. Okay. Any questions about this idea? Okay. So yeah, so here is like kind of here are some of the things which are kind of like some key points to remember. So the probes are basically the blinking fluorophores are also called probes. So the photoactivatable and photo-switchable fluorophores are probes, and they should have large extinction coefficients at an activation phase. So basically, like this speaks to how efficient they are. So large quantum yield means, like say some light falls, what is the probability that it emits a photon, right? So for making a measurement, it has to have large efficiency. If it's a very weakly scattering or weakly fluorescing kind of a sample, it's not good, because you want like sort of you want to do it fast enough that kind of you rapidly you take one image after another image after another image, and so the disadvantage is it takes a lot of images to collect that one full super resolved image. So that's kind of the penalty you pay. So having a high quantum. So its extinction coefficient is basically like say if light falls, how much of light gets absorbed. Okay, and this quantum yield means how of the light that is absorbed, like how much is emitted back, how much is comes like what fraction comes out. Okay, those are all important. So, and then it should have a reduced tendency for self-aggregation, meaning you want it to be far apart, right? These dots. If they are all clumped together within one blob, then the assumption that there is one dot inside that region breaks down. Therefore, if they all self-aggregate, if they come close to each other, that's a problem. So you need some molecules which kind of stay far apart naturally for this to work. Uh, and low but finite photo bleaching. So the photo bleaching, so as I mentioned, like kind of over time the fluorescence degrades. You don't want it to degrade so quickly that kind of you can't make enough close measurement. So photo bleaching has to be relatively low for this to work. Okay, so those are some of the kind of key points for this approach. So this was 2D, right? Like I was showing an image, kind of, so you can get data, very good data in 2D with this kind of an approach. And people extended this to 3D. And so how do you extend this to 2D? Another person came up with a very clever idea, which was use, sorry, yeah. So you have you have the sample. If put a 4F kind of a system, that way in Fourier optics we study this. In the Fourier plane, put a face mask, a piece of glass which has a certain kind of pattern on it, basically, or a certain profile of glass. Okay, put a face mask such that it will take a circular beam and create a helical beam. So in other words, it's like two dots. Imagine two dots, and as you move it, you rotate the dot, right? So like if you have two dots and kind of like if you keep rotating it and imagining along Z, if you move the two dots along Z and rotate it, what happens? You get a helix, right? So that is so the reason why that's useful is if like instead of it being one dot here, if you have a pair of dots, if it is in one Z location, it's these dots. If it is at a different, like if you measure these two dots this way, then it's a certain Z location. If the orientation is this way, it's at a certain Z location. So different pairs of these dots, when you look at how these dots are, what is the angle of these if you draw a line, what is the angle of that line? Then you know the Z position. The Z is converted to an angle. And this way, so if it is this kind of the two dots are in this kind of orientation, it's one Z location. If they are over here, this orientation is one Z location. This location is one Z direction. This one. So basically, it tells you that by looking at where these two dots are created with a face mask. So it takes one dot and makes it into two dots. So that's the function of that face mask. And so you can make a face mask of that which does this transformation, which has this transfer function. And then different Z positions correspond to different kind of these shapes. And this way, and then you do the exact same thing as before. Okay, except for instead of you having a circle and finding the center of the circle, you have two dots here, find the midpoint of the two dots. And the rest is essentially the same idea. Okay, and so this way you can get Z, X, Y, and super resolution along Z as well. And so this, this allows you to get images of the sort here, where so like blue is like 0 level, and then 10 is the 10 microns high is the red color. Okay, so in different colors corresponds to different heights. So it's in 3 dimensions. If you can imagine this in 3 dimensions, so these are different kind of what look like fibers, which basically are kind of in 3D, and these parts are high, and this side is low, and there are low and high things inside in this region. So you can see the networking of fibers in 3 dimensions. So like these are kind of so thin that you can see it here. Okay, so it's about 10 microns, and they are like in confocal, you will not be able to see this kind of this regular confocal, but the super is all 3D version. You're able to kind of get this these kind of images. So this is the PS, what's called the PSF design idea. So the point spread function, you create a mask so that you kind of it's called point spread function engineering. So you make a point spread function, instead of it being a circle, you make it a helix, and different positions along the helix have different properties. Any questions? Yeah. So the last big kind of imaging idea that I want to talk about is shed microscopy. Okay. So here the this is Stefan Hell. So the previous one was by Eric Betzig, like the idea of this blinking fluorophore. That's like one of the 3 Nobel Prizes winners that I mentioned earlier. So this is Stefan Hell, who is a German kind of scientist. He came up with this a very different way of doing like super resolution, which is here you have, instead of one laser, you have 2 lasers. So you have one laser which is falling on a sample. You have a second laser which is also falling on a sample. The difference is that the first one is just like a regular like confocal or any other beam, a circular Gaussian or circular beam which falls on the sample. The second beam is special. It's a shed laser where it is like a donut shaped beam. Donut shape or vada shaped beam, like basically there's a hole in the middle, right? So basically you have a circle and then you have this kind of beam where there's a hole in the middle. So one of them excites this entire like circle. Then the second beam pushes down the kind of fluorescence, like stimulated depletion. So it pushes down the electrons in that donut or vada shape. So only the molecules, fluorophores in the middle remain. And so the spot size becomes the size of the hole. Does that make sense? So you have, let me kind of show this here. So you have an excitation beam, which is like this circular Gaussian or circular shape for now. Then you have this kind of a like donut beam. Then this excites the molecules at all these places. This pushes down the molecules. What remains and has fluorescence is a much smaller spot corresponding to the hole inside in the middle. And so this is the idea of shed, okay? Shed microscopy. So this way you can get much smaller compared to if you have, this is a diffraction limited spot, you get a small spot. So this is the size of the, if you didn't use this idea, you will get a blob of this size. But with the shed idea, you basically make it this size. You make it much smaller. So and then you move this dot around the sample and you get your like 2-dimensional imaging. And they have extended to 3D as well, but the basic idea is the same. Okay, so basically you have 2 beams which are kind of coming together. One, so this is a fluorescence. So one excites the fluorophores, the other depletes the fluorophores in a nonlinear fashion, and this de-excitation beam results in a fluorescence of this side. So yeah, so here is like so this is the 0 point. Effectively, the point spread function is much smaller than the actual diffraction limit of your lab. And so people have done a lot of very interesting and cool experiments with this. So typically excitation is this one color light and another this shed beam is the second one. You focus it onto a very small spot. You can do imaging. You can have a biological sample, for example, here. You can do imaging with this one, and you move the sample or move the point around and get imaging. So the kind of resolution. So if you look at this with the regular imaging system, you can see it's much better resolved. So you can, what used to be a big blur has become much smaller point with this with the resolution improvement of shed. Okay, to give you a different example, which is much more obvious in a biological system, which these are called microtubules. And so basically, inside the cell, there are these microtubules. So, like instead of this being like the image with a regular confocal microscope, you have the STED microscope, where as you can see, it's much thinner, much finer details. You can get much, so you get super resolved images with STED microscope. And yeah, and then you also have like this, here are a few more examples of the kind of confocal and STED. You can see much finer biological samples. So firstly, in the first few experiments, it was done on dead cells or not living cells, but people have extended to living cells as well. And you can this is uh, like getting the precise alignment between the two beams is a very difficult. It's not an easy thing to do, but people have figured out how to do this, and it works remarkably well. In fact, people now buy, you can, companies sell instruments of this sort. It's expensive enough that again one university may have one or like two, and people share it as a use like a shared facility. And so related version is, instead of like the excitation can be a like sort of, instead of it being a dot, it can be a plane. It's called selective plane illumination. So the illumination can be a plane from the side. You have a plane of illumination, and then everything else, the fluorescence detection and other things can be from the other side. So perpendicular. So excite one plane of light with a sheet of light, and then measure from the perpendicular direction or some other direction. So that gives you good imaging data as well. So I won't go into too much of this, but these are some of the ideas that people have come up with. To kind of give you a overall summary of all these, that super resolution, how to compare so these ovals correspond to the point split function, the size of the spot you can see. So regular confocal, it is something of this size. Okay, so blue is small and red is bigger, right? Because of the wavelength lambda by 2Na. And so this is the confocal, how much you can, what kind of resolution you can get. And then if you look, these are the super resolution methods which go beyond the smaller than this kind of regular confocal, and you can get structured illumination which doubles or halves the size of this in different dimensions. So this is that structured illumination, 2D, this 2D and 3D. So those are slightly different. And then the STED is over here, and then the palm storm and the other, the blinking version are over here. This is the size of the spot you can get. Okay, so basically, this is the size of what the 2D. This is 2D and this is 3D. So 3D and 2D, how much you can localize with these super resolution methods. So compared to this is the size of the single dot you can precisely localize and you get an image of. Here are some lot of different applications of wide field structured illumination, STED, and so on. The palm storm, like certain things for biologists and people in medicine and biology use this quite often for all different kinds of building all different kinds of imaging systems. So, and this brings me to the end of the course, roughly. So, in conclusion, this is all I had to say about super resolution and all the different imaging methods. So every single idea that people came up with, they were able to use it to make an imaging system, and as you can see, some of them can be extremely powerful and very useful. And I hope at the end of this GYAN course, you found that this course was instructive, exciting, and also hopefully inspiring. And I hope that you, at least many of you here, could develop new ideas and for instruments, and that could perhaps revolutionize medicine and biology. And if you can if you keep trying, as in most of these things didn't happen overnight. It took a long time for people to come up with, they came up with ideas which didn't work, and eventually they came up with some brilliant idea which worked wonderfully. So I hope you start thinking along these lines, thinking about how to new ideas for making new instruments, you could potentially succeed. Second thing is, in this over the course of the past 10 lectures, I first try to give you a foundation, like give you all the foundational concepts in optics and photonics. I hope like that lays a foundation for you to study or learn anything else in the future. And I gave you some of the ideas that were instrumentation ideas and the details of how many of these imaging systems that people have built, how they work, what were the key concepts and ideas, especially with a focus on infrared imaging. We talked about OCT and mid-infrared imaging and so many related imaging methods. And I gave you examples of a lot of biomedical and biological applications, clinical applications, and biological basic biology applications as well. And we covered a large breadth of topics, and I hope this was, as I said, instructive as well as inspiring. That's it. Thank you all, and thank you for coming to this Gyan course, and I hope you enjoyed it. Thank you.